Okay. Oh, here we go. All right. Can I assume everybody can hear me?
Yeah.
Yeah.
Okay. Before we get started, any problems last night with the post lectures?
No.
No.
Okay. Did everybody get them uploaded into GradeScope? Okay.
Yeah.
Mm-hmm.
I will today.
Okay. So I was able to go through, and I mean, yeah, for post lectures 1 and 2, just kind of quickly glancing at the submissions that were there, it seems like we're okay. The only thing that kind of popped up was a couple of you gave a definition of heat that didn't mention temperature at all. And that's an important distinction. Heat is an energy transfer, but it's an energy transfer that's the result of objects being different temperatures, and the hot object transfers energy to the cold object. That's what makes it different from internal energy or kinetic energy or any of other hosts of energies that are out there, because that energy is specific to temperature differences. But that was really the only thing that jumped out at me as being out there and odd and kind of out of place. Any other questions about what's going on before we get started today?
No.
Okay, so let's get into our stuff for today. Let's start by reviewing a little bit of what we saw yesterday. So I've got 3 panels here. Which of these 3 panels, which of these 3 circles, A, B, or C, would represent liquid nitrogen?
I'd have to say C.
Okay, I hear a C.
Also C.
Okay. Okay, and that would be correct. C is liquid nitrogen. Now, there's 2 things that we can tell about it that would lead us in that direction. First of all, nitrogen is one of our diatomic elements. Now, if you look at any periodic table, the diatomic elements are easy to find. Basically, it is hydrogen, and it is the nonmetals that kind of form a 7 on the periodic table. So starting with nitrogen and working your way over to fluorine and then down the rest of the halogens. Those are all of your diatomic elements. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, those are the ones that will naturally pair up with themselves. And we talked about this a little bit yesterday, the idea that nonmetals tend to form molecular compounds in their elemental states. Some form diatomics, like the ones that we just talked about. Things like sulfur and phosphorus, carbon tend to form more molecular solids. For example, carbon can form like 60 and 120 membered chain rings and balls. The field of nanotechnology is largely based on this. But we can also see that things like, phosphorus tends to form four phosphorus compounds. Sulfur tends to form 8-membered rings. It's just, that's how they kind of work. So C is our liquid nitrogen. Now, of A and B, which one of these would represent solid dry ice?
That'd be A.
And what makes you think A there, Brett?
Basically, just because the way the molecules are structured, they're more organized, they're more compact.
And that's exactly right. So as we talked about yesterday, we see with solids close packing and organization. We can see that for the most part, I mean, it's not a perfect crystal here by any means. The arrangement here is a little bit disordered in places, but overall it's pretty organized, which means that the last part here, this is our sublime dry ice in panel B. And what phase of matter would we say that is present there?
It'll be physical.
So what phase of matter? Yeah, what physical phase is our sublime dry ice? Solid, liquid, or gas?
It's going to be a gas.
Yeah, yeah. This would be a gas. So again, just looking at the differences here, this is what our depiction of a liquid was. We see in that depiction of a liquid, we've got pretty close packing, but disorganization, some spacing in between some of the molecules. Here we've got significant amounts of space between those carbon dioxide molecules and each other. And so they really don't interact a whole lot. This is a gas that we're talking about here ultimately. Now, the primary focus for today, and we'll break this probably up into two pieces, maybe three. Third piece, we might just do a whole bunch of practice problems. Our primary focus today are units of measurement, and then just kind of reviewing how we convert from one unit to another, how we do some simple calculations in science and in chemistry. And that's going to be really important to us because once we get through some of that material, we're going to be starting chapter 2 tomorrow. And once we get through some of this stuff, a lot of the calculation stuff that we do, a lot of the things that we kind of are, chipping away at and working on, you're going to need to know how to work with numbers. It's going to be important when you do your laboratory activities. It's going to be important when you do your lecture activities. It's just going to be something that comes up again and again and again and again. So we're going to take today and really make sure that, you've probably seen this, but let's make sure that we've got it down and that we know how to work with numbers, how to work with calculations, because that's really going to make all the difference in the world to us. So when it comes to experimental results and looking at things, the primary system that we use in the sciences is called the International System, the SI system. And the primary reason for this, now you may have heard of this system. It's commonly referred to as the metric system. It's not actually quite the same as the metric system, but how it's derived is essentially the same. Everything's based upon units of 10, about ideas of based units and derived units. The metric system has a slightly different base unit system in terms of the primary base units there, meter, liter, kilogram, or excuse me, meter, liter, gram. Whereas the base system does not include volume. The SI system does not include volume as a base unit because it is not a base unit, it's a derived unit. So there are small nuances there, but they really are talking mostly the same language. Now, in your assignment for last night, we saw that there were 6 base units that we needed to worry about. There is the meter, there is the kilogram, there is the mole, the ampere, the candela, the Kelvin temperature, and one more I'm forgetting, but nonetheless, you had to write down those base units, and then from those base units, what we can do is we can derive other units out of those. So, for example, volume. Volume is not a base unit. Volume is considered a derived unit. Now, why is it considered a derived unit? Well, it's considered a derived unit because we can derive it. We can build volume out of other base units. So the base unit in this case is distance, which is meters. And if I take distance times distance times distance and get a cubic measurement of distance, I would get a volume. And so for that reason, we cannot consider volume a base unit. It is a derived unit under the SI system. Similarly, energy is a derived unit. The unit in question here is something called a joule. And the joule is derived by taking the base units of kilograms, meters, and seconds. Seconds would be the unit I forgot about, the unit for time. And taking kilograms times meters squared, dividing it by seconds squared, that would give you joules. That would give you a unit of energy, a unit that can measure how much work is needed to be done to perform some kind of a task. So here are our base units. Now, I made mention before, there is another base unit out there. There's actually a 7th one. It's called the candela. Candelas are used for measuring the intensity of light. So if I want to know how intense, how bright a light is, candelas are the way to do it. And actually, we see candelas used often. If you've ever had to buy light bulbs, on the package, there's always two units on the light bulb. There's always wattage, which is how much power is it going to use. Gives you an idea of, okay, there's a certain finite amount of power that I want, or that my circuit breaker is capable of using. And sometimes that's important. But more often than not, when you're buying light bulbs, you're interested in how bright is it going to make this room. And that's where candelas come in. One of the differences between soft white light and daylight kinds of light bulbs has everything to do with, well, what are you trying to do? Do you want a really bright room? Then you're going to look for something that has a brighter white light, more candelas. If you're looking for something a little bit softer, like maybe in your living room or in your bedroom, where you don't want the bright fluorescent kind of appearance, then you're going to go for like a softer white light bulb or something like that. So candelas are used in that regard. And they're a very common unit for that reason. Now we won't use them in this class because we really don't do anything with light intensity, but it is there, and that is something we would use if it was something we were going to study. But the other base units here for mass, the base unit for mass is the kilogram. Again, this is where it differs from the metric system. The metric system would have the base unit here as the gram. Base unit of distance or length is the meter. The base unit of temperature is the Kelvin, and again, differs from that the Celsius system, which would be common in the metric world. Base unit of time is the second. Base unit of current is the ampere, which we won't really talk a whole lot about in this class. But if you take Chem 2, amperes become very important when you learn about electrochemistry. And then finally, quantity. For that, we use the mole. And I'll just give you a little sneak peek here. Pretty much, let's say, 65% of the calculations that you're going to do from chapter 2 on are going to involve moles somehow. It's probably our most common unit because it is the unit that allows us to compare quantities of substances directly. So you're going to see it a lot. Now, this is the table of prefixes. Now, the table of prefixes for the SI system, for the metric system, is massive. Far more massive than what you really need to know. What I tell my students is that really you should be able to focus in between these two red lines. If you can accurately depict the relationships between these units and the base unit and these units and each other, then you're going to be on the right track. And these prefixes, these numerical associations, are things that you're going to be responsible for knowing. These are not going to be provided in any reference table. These are not going to be provided in any kind of supplementary material for any of your quizzes or your tests. You need to know these. You need to know how to use them. Now, for the most part, you're familiar with a number of these already. You're familiar, considering that you're watching this video right now, you're familiar with the concept of megabytes and gigabytes. That's how you measure internet speed. That's how you measure capacity on your computer. That's how you measure a lot of things that are technology and bandwidth related. Now, giga, which is outside of our red lines, but a well-known unit, is 1 billion times the base unit. And so if I have a gigameter or a gigabyte, that's 1 billion times larger than a byte, or 1 billion times larger than a meter for a gigameter. Mega is 1,000,000, kilo is 1,000. Hecto and deca and deci, we really don't see a whole lot of use for. In most cases, we usually ignore them. The only time we really don't, deci gets used a little bit because a cubic decimeter is equal to 1 liter. That's really the only time we ever use that unit, use that prefix. But these other ones here, centi, we talk about centimeters often, millimeters. So we're now talking about 1/100th of a meter, 1/1000th of a meter. For micro, nano, pico, now we're getting into smaller scale kinds of items. So we're talking about things on the well, not necessarily the atomic scale, but the molecular scale, the cellular scale, when we get into micro and nano. For the atomic scale, that's more in the pico range, 10 to the -12th. For Subatomic particles, if we're looking at how big is a neutron, how big is a quark, how big is an electron, that's usually on the femto or atto scale. But again, not too often that we'll see those. In fact, really the only time I talk about pico or any of the others is as a reference in talking about atomic size. So again, if you can stick in between these red lines, this is really where you need to kind of focus yourself and look at the units themselves and the prefixes. And just keep in mind that the values here are relative to the base unit. So a kilo something is 1,000 times the base unit. So 1 kiloliter is 1,000 liters. 1 micrometer is 10 to the negative 6th meters. And so, especially when we're doing unit conversions, it's important to recognize what the relationship is. I see it quite often where students use a table like this to try to do calculations, and they end up making mistakes because they misinterpret what it means and do things like saying that there are 1 million megameters in a meter, or 10 to the negative 9th nanometers in a meter. And that's not what this is saying. It's the opposite. So just kind of keep that in mind as we start looking at some of the units and conversions. Moving on to temperature. Now, temperature is the direct measurement of heat energy. So temperature isn't energy itself, but it's a way that we can measure how much energy an object has. So when we have something that has high temperature, we know that that something is going to have lots of internal energy, and that's usually manifested in terms of kinetic energy. So when we think about the subatomic particles in a sample that has a high temperature, we can think about those particles moving very, very, very fast. Whereas if we have something with low temperature, that usually means a lower energy. That means that the molecules are moving slower. Now, when it comes to temperature, temperature has been studied for centuries, and I do mean centuries upon centuries upon centuries. But the 3 most common temperature scales are attributed to Fahrenheit, Celsius, and Kelvin. Now, the Fahrenheit scale was introduced for primarily using devices where a liquid inside of the device would expand upon heating, contract upon cooling, and so you put it into a small enough space, and the expansion or the contraction causes the liquid inside to go up or down. That's the basis of a thermometer. Celsius, on the other hand, used his scale and defined on that scale the freezing point of water and the boiling point of water. He said that the freezing point was going to happen at 0 on his scale. The boiling point was going to happen at 100 on his scale. And then every other temperature that was listed would be relative to those 2 values. And then Kelvin based his on the lowest limit of temperature. So what he did was he said, okay, there's a definitive 0 point, absolute 0. And at absolute 0, that definitive point, that's when there's no motion. That's when there's no energy. And so if we use that as our basis for starting, then every other temperature can be made relative to that 0 point. You just make a big old linear scale based upon the energy of the particles compared to what it was like when there was no energy and there was no motion. And so those 3 temperature scales have at their impact a couple of key important things. So first of all, if we compare all of the scales side by side by side, what we will see is that the Celsius scale and the Kelvin scale line up absolutely perfectly. And what I mean by that is if I take these 2 points here, the melting point for aluminum foil, the boiling point of water, if I take those two and compare them, I can see that there is a 560-degree difference on the Kelvin scale. There's also a 560-degree difference on the Celsius scale. And so what's actually kind of interesting about these is that the Kelvin scale and the Celsius scale are scaled the same way, just with one important difference. And that one important difference is this correction factor right here, 273.15. The Kelvin scale is basically 273.15 degrees higher than the Celsius scale is. So it's like they're the same scale, but one starts up higher than the other. And so converting between Celsius and Kelvin is actually really easy. All I need to do is take that Celsius temperature, add 273.15 to it, add 273 to it usually, depending upon how good our thermometer is, and that would give me Kelvin. And by contrast, if I look at the Celsius scale versus the Fahrenheit scale, I see that there are some slight differences. So let's compare this time the boiling point of water versus the freezing point of water. And so we can see that for the Celsius scale, there's a 100-degree difference between the two. But on the Fahrenheit scale, there is a 180-degree difference between the scales. Other than that, and the fact that we are 32 degrees off of 0 on the Fahrenheit side, the two scales are pretty close to the same. And so this is a little bit harder of a conversion to make. If we want Celsius, we have to take the Fahrenheit temperature, subtract 32 to account for that 32-degree correction, and then multiply it by 5/9. Now, why 5/9? Well, 5/9 is the manifestation of this ratio between Celsius and Fahrenheit. And so if I take the temperature differences here, 180 divided by 100, I get 1.8. And so if I was going from Celsius to Fahrenheit, I would need to multiply that value by 1.8 to account for the scalar difference between the two. But if I go the other direction, 100 divided by 180 to go from Fahrenheit to Celsius, well then, all that's missing there is, well, that's 10 out of 18, which would be 5/9, or in decimal form, it's about 0.555. So that's where the 5/9 comes from. Now, this is the way that your book gives the definition. It's not my favorite way of showing this. I actually prefer to use the 1.8 because it's easier to look at. And so if we wanted to, we could rewrite this equation as Fahrenheit minus 32 divided by 1.8. And that would give us Celsius. And then just using a little bit of algebra to flip it around, (1.8) times Celsius plus 32 would equal Fahrenheit. So two different ways of looking at things. I prefer this way just because dealing with fractions, it's not my favorite thing to do. And when the decimal number is just so easy to work with, that's the way I prefer to go. But that's how we can do the temperature conversion. All right, so let's do a quick practice problem where we do a conversion of this type. Temperature of coffee from the student union is found to be 205.43 degrees Fahrenheit. Now, first of all, let me say, if you take the temperature of coffee from anywhere and it is that hot, that's a lawsuit waiting to happen. That's stupid hot coffee. That is third-degree burns on your lips and tongue kind of hot. There's a how many of you are familiar with the McDonald's coffee case from the 1990s?
I am.
Not me.
Okay.
Not me.
Okay. There's a famous lawsuit from the 1990s, and it's always kind of brought up as oh, isn't that a stupid lawsuit kind of example. It involves an old woman. Forget what her name is, but she went to a McDonald's in her town and ordered a cup of coffee, and put it in her lap, and went to hand her grandson or something in the back seat something, and the lid on the cup of coffee failed, and the coffee basically spilled out into her lap all over her legs. And she sued McDonald's, not because the coffee was mislabeled or anything like that. She sued because the industry standard for coffee at that time was right around 200 degrees Fahrenheit. And the boiling point of water, just keep in mind, is 212 degrees. So we're talking about, stupid hot coffee here. And she actually won her settlement. And the kind of the key factor in that was within, I want to say, 1 to 2 minutes of spilling the coffee on herself, she had contracted third-degree burns on the inside of both of her legs. Through appeals, McDonald's won back most of their money. The woman ended up dying near bankrupt. It's kind of a sad story when you look at the whole perspective of the thing, but the thing that came out of it, other than the lawsuit and other than the late night people making fun of the lawsuit, was that the industry standard was changed. It was deemed, the reason why the woman won the lawsuit in general was because the jury, the judge, and all involved agreed that 200 degrees was too hot to be serving coffee to people, and that standard needed to be changed for the health and benefit of the consumers. Just a little interesting side story there. Like I said, if you pull out your thermometer at your favorite coffee shop and that's the temperature that comes out, you got a problem on your hands. You got to cool that thing down, way down. But to the problem at hand, we have 205.43 degree coffee. Oops. So to turn that into Celsius, remember Celsius is equal to Fahrenheit minus 32 divided by 1.8. So 205.43 minus 32 divided by 1.8 is going to be our calculation here. And so if we punch that into our calculator, a small word about significant figures here. We haven't talked about them totally yet, but exact numbers like the 32, which is a defined value for the freezing point of water, those have infinite precision. So out of the subtraction, we're going to keep as many decimal places as go in. So 205.43 minus 32 will give us 173.43 divided by 1.8. 1.8 is also an exact number, 180 divided by 100. So we get 96.350 degrees Celsius as our mark there. And so again, where the sig figs come from there, I've got 5 sig figs off of the temperature. I've got nothing here. These are all exact numbers, so I should have 5 significant figures coming out of the calculation at the end. Now to turn that into Kelvin.
Mr. Brock.
Yes, Chassie.
So when I did it, I got 96.35.
Yes, did I say 5.3?
No, you said the 0 at the end. Like, it didn't pop up on my calculator.
Okay, so that happens from time to time. If your calculator is always going to round, your calculator does not do significant figures. No calculator does.
Okay.
So if it comes up with fewer digits than what you need, you can assume that the remaining digits are zeros that you can add on to the end. Just
Okay.
make sure that you don't add on digits that don't make sense, if you understand what I'm saying. So, you know, if the number is 2,000 and you need 5 significant figures, don't make it 20,000 to make it boot. Make it 2,000.0.
Okay.
Okay? Don't change the value of the number, but change the number of digits that represent that value.
Okay.
Okay? Last bit here, because we've got about a minute left. Kelvin is equal to 273.15 plus Celsius 96.350. And that would give us 369.50 Kelvin. Okay. Now, in this case, we have to use decimal places. Our Kelvin our Kelvin conversion has 2 decimal places. Our temperature value has 3. We always round to the fewest decimal places when we add. So we had to round this to 2 decimal places here. So 369.50 Kelvin is our answer. So